Assalamualaikum warahmatullahi wabarakatuh, and have a nice day to our lecturer for the Water Reticulation Department, Dr. Erwan Hafizi bin Kasiman. This video is my major presentation for the Water Reticulation Department for the subject of Integrated Design Project 1. First of all, before I start my major presentation, I would like to introduce myself. My name is Nur Dhiyaulhaq bin JAMALLUDIN, and my metric number is A19EA0122. My partner that has been working with me this whole time for this department is Kelvin Oscar Hamphrey, while for the other department, we have Adam Daniel and Shakir Aiman Daniel in the erosion and sedimentation team. We have Eng Hock Sang and Ji Sheng Ze for the earthwork department, and lastly, the cost and estimation department, which has been managed by Lydia Afrina and Vivian Harry. Let me start my presentation by giving a brief explanation on what is meant by water reticulation. Water reticulation is the process to transfer water from the tank to the area. This process helps provide clean water for the usage of daily life and fire hydrants to provide safety for the area. In water reticulation, there are many components that make up water reticulation. Water reticulation system piping system consists of a network of pumps, pipes, and water tanks that are designed to supply and distribute water to domestic areas such as condominiums, hotels, commercial lots, buildings, facilities, and factories with sufficient pressure and quantity to consumer within the water demand supply. In the integrated design project, our tasks are to design a suitable water supply system for the light industrial area. The design of the area is based on the Suruhanjaya Perkhidmatan Air Negara (SPAN) and the Malaysian Water Association (MWA). The guideline will provide a suitable flow for the design process of the provided area and also provide a criterion that is required to be fulfilled after the design is complete. The objective of this water reticulation project is firstly to calculate the water demand of the allocated area, and then we have proposed a suitable design of water tank capacity to fulfill the demand. After that, we determine the flow rate in the pipe, fulfill the suitable residual pressure head, determine the optimum piping size, and lastly, determine the height of the storage water tank. So this is our proposed loop layout for the water reticulation flow. As you can see, the layout of the area is split into two regions. We name it the northern region and also the southern region. From the information we got from the earthwork department, we know that the highest reduced level is located around the upper left part of the layout, which we will use to put our water storage tank. However, due to the distance from the tank to the far right of the region being excessively far, a very high number of pressure heads is needed, which exceed the limit we said earlier. Therefore, we divide the area into two parts. Each has their own set of water tank. This will fulfill the required residual pressure and the unit head loss. This first plan shows the flow of the knot and which section will the water be provided. The information about the loop is as shown in the legends above. Firstly, the water tank is indicated by the white circle. The green arrow shows the direction of flow, and the node is indicated by this yellow circle. Overall, this layout consists of 25 nodes, 21 pipes, and a total of 8 loops, with 5 loops in the northern region and the other 3 loops located in the southern region. And this second plan shows the location of the fire hydrant along the lines. By referring to Malaysia Water Association Design Guideline for Water Supply System, this proposed is used for light industry, thus considered for Class C risk, which means a maximum number of 1 fire hydrant is needed for every line of water piping flow. Closed-loop pipes network is used to analyze the reticulation pipelines for the project. By using this network, water supply could reach every commercial lot even if a part of the pipeline is closed for maintenance. Besides, enough water is available for the fire hydrants, as the hydrant draw water from the various branch lines due to interconnections. Water is available at every point with minimum loss of head. Before we can proceed with the necessary analysis, we must first calculate the water demand needed for that particular area. The water demand for each node is computed according to the tabulation of estimated water demand rate for planning of external water reticulation by Suruhanjaya Perkhidmatan Air Negara (SPAN), According to that, most of the buildings located in the proposed area are under the category of light industry, with the water demand of 33,000 litres per hectare. The water demand is determined based on one-day storage, and it is based on the type of premises. Besides, the average water demand or the average flow rate in pipe approaching each tank is determined based on the total storage volume in the tank per day in liters per day, and then converted to meter cube per second in the design calculation. Since we have divided our area into two regions, we also calculate the water demand for each region separately. The calculation of water demand is divided by each node. The important part that we need to focus on here is the total water demand in terms of average flow, peak flow, and also the fire flow. To get peak flow, we multiply the average flow with the coefficient of 2.5, while for the fire flow, we multiply the average flow with the coefficient of 1.0, or in other words, the fire flow is the same as the average flow. These three values will then be totaled up and be used later during the design of the water tank. Therefore, for the northern region, the total water demand in terms of fire flow, we got it to be 499.77 meter cube per day, while for the peak flow is 1249.43 meter cube per day. For the southern region, the same method is used, and we got the total water demand in terms of fire flow to be 406.73 meter cube per day and 1016.83 meter cube per day for the peak flow. If we compare this value to the northern region, we can see that this region requires less water demand since it has a lesser number of light industrial buildings compared to the northern region. From this value, we can already estimate that the value of residual pressure head for this region will be lower compared to the northern region, thus may require a lower number of water tank design, lower height of water tank design. Next, I would like to continue by discussing the software that we use to ease our calculation process throughout this project. This software is called EPANET. EPANET is a computer program that simulates hydraulic and water quality behavior. EPANET is a computer program that simulates hydraulic and water quality behavior in pressurized pipe networks over a long period of time, developed by the United States Environmental Protection Agency's Water Supply and Water Resources Division. Pipes, nodes, pipe rotation, pumps, valves, and storage tanks or reservoir make up a network. EPANET monitors the flow of water via each pipe, the pressure at each node, the height of water in each tank, and the concentration of a chemical species throughout the network over the course of a simulation period that includes numerous time steps. These will help to check the important fulfillment criteria such as velocity, residual pressure, and unit head loss. This computation will be done for both peak flow and fire flow to check both the design will be up to the standard of the SPAN and MWA guideline. This is the example of the figure that is being used in the EPANET software to do the computation. The above one shows the value of the pressure head in terms of fire flow, while the bottom one shows the pressure head in terms of peak flow. As I have mentioned earlier, our water reticulation system must follow the guidelines specified by MWA and SPAN. MWA stands for Malaysia Water Association, while SPAN stands for Suruhanjaya Perkhidmatan Air Negara. These are the guidelines that have been specified by the Malaysian government for various reasons. To make sure we get the most economical and safest water reticulation design system, we try our best to follow both guidelines in conjunction to each other. All the important values such as the velocity of water, the residual pressure head, and also the unit head loss is compared with the values specified in both guidelines. Firstly, we need to make sure that no water exceeds the maximum velocity of 2 meters per second. This must be taken into consideration in order to prevent any erosion taking places inside the pipeline, thus making sure the pipe can last for the desired period of time. After that, we have to make sure that the pressure head does not exceed the maximum value that has been specified in the guideline, which is 30 meters. This is due to the reason that the pipeline may be at risk to burst under the excessively high pressure. Actually, when we first tried to design our water tank, we only had one water tank. However, the value of the residual pressure head became too large. Therefore, we needed to redesign our tank and decided to separate into two tanks in order to get the lower pressure head value. The other alternative would be to use a specialized material for the pipeline, but that will be at a higher cost, which is not in our favor. Last but not least, I wanted to mention that the minimum amount of pressure head needed at the first node is based on what we have calculated must be at least 7.5 meter to make sure water demand can be supplied to the whole node in the entire region. Next, we move on to our proposed water tank design. It is very important for us to think thoroughly about the water tank design since we need to insert the value related to the water tank inside the EPANET software to do the computation process. A good design can ease the burdens of our calculation afterwards. Firstly, like what I have said just now, we decided to separate our water tank into two regions since the value of the pressure head is too large to make a single water tank. A few trial and error process have been made by me and my team member to get the best design that fulfill our desired criteria, and at the end, this is what we recommend. Firstly, for the northern region, we recommend using a grounded water storage tank with a circular shape made of fiber reinforced plastic. This is due to the fact that the reduced level is already high and there is no need to make the water tank higher. We propose the diameter of the water tank to be 15 meter with the height of 8.3 meter in order to satisfy the desired volume and pressure head of water demand needed. When the tank is in full condition, the top water level is calculated to be 83.3 meter and the bottom lower level is at 75 meter. The volume of this water tank is designed to be 1466.73 meter cube in total. Whereas for the southern region, we recommend to use an elevated water storage tank with a circular shape made of fiber reinforced concrete. Unlike the water tank from the northern region, these tanks need to be elevated since the reduced level is too low. Therefore, it is not enough to make a grounded water tank. We propose the diameter of the water tank to be 15 meter with the height of 8.3 meter in order to satisfy the desired volume and pressure head of water demand needed. When the tank is in full condition, the top water level is calculated to be 68.73 meter and the bottom lower level is at 17.18 meter. The volume of this water tank is also designed to be 1466.73 meter cube in total, same with the northern region. After we have inserted all the necessary values inside the EPANET software, we can run the analysis to get the important values needed and to do the necessary checking to make sure it is within the set limit. The left side is the node analysis, which shows the pressure head values in each node. Based on the value provided, we can see that all pressure heads are within the set limit, which is below 30 meter. While for the right side show the computation of the pipe analysis, which shows the velocity of water and also the head loss in each pipe. From the data generated, all unit head loss is found to be below the limit set by the guideline, which is lower than 2 meter per kilometer. And this one is the analysis of peak flow using EPANET. The same procedure has been taken, while the only difference in the value of water demand is multiplied by the coefficient of 2.5, while all the residual pressure head and unit head loss were found to be lower than the set limit. We can conclude that our water tank design is adequate and suitable to be used in our water reticulation system. In conclusion, I would like to recap that we have divided the area into two regions, the northern and the southern region. By referring to the guidelines prepared by SPAN, the computation of flow analysis has been carried out using EPANET and the most economical tank design has been proposed. For the northern region, we recommend using a grounded water tank with a diameter of 15 meter and a height of 8.3 meter to meet the total demand of that region. Whereas for the southern region, we propose to use an elevated water tank with a diameter of 50 meter and a height of 8.3 meter. The residual pressure head for the northern and southern region is 14.8 meter and 24.2 meter respectively, which is higher than the minimum residual pressure head, which is 7.5 meter. Thus, the usage of pump is not required. Therefore, we can conclude that our design of tanks for the water reticulation system in both northern and southern regions is adequate and suitable to be applied in the proposed project. With that, thank you.